In this video we're going to look at chemical equations, which we use to represent chemical reactions. Now there are two main types of chemical equations. We have word equations and we have simple equations. So here we have the word equation and the simple equation for a neutralization reaction between calcium carbonate and hydrochloric acid. And what we're going to do is to simply compare the two types of equation as to what they actually show us, what they have in common, and what they have that is different. So we have our word equation and our simple equation. So we'll start with what's similar. So they both very clearly tell us what the reactants are. They both tell us that there's calcium carbonate reacting with hydrochloric acid. They both tell us what the products of the reaction are: calcium chloride, carbon dioxide, and water. Now the word equation is a simplified or simple expression. That is all it tells us. It tells us what the reactants are, it tells us what the products are, and there's no more information you can really take from that. Whereas the simple equation gives us quite a bit more detail. So for example, it tells us the quantities of each substance that are going to react or be produced. It tells us that one calcium carbonate reacts with two hydrochloric acids to produce one calcium chloride, one carbon dioxide, and one water. You can't tell the ratio in the word equation, but in the simple equation you can. So we have the quantities of each substance. In the simple equation we can very clearly see every element present: calcium, carbon, oxygen, hydrogen, chlorine. So we can see each element. We can see how many of each element. So there's one calcium here, one carbon, 3 oxygens. We've got 2 lots of 1 hydrogen and 1 chlorine. So you can see the total number of everything. So we can see the quantities of atoms for each element. And that is both in the individual substances but also overall. And finally, these bits in brackets here, S, AQ, AQ, G, L, those are state symbols. So we can see the states of matter for each of our substances. So we can see that calcium carbonate is a solid, hydrochloric acid is aqueous, meaning dissolved in water, calcium chloride is aqueous, dissolved in water, carbon dioxide is a gas, and water is a liquid. So there are a number of different reactions that you could be asked to write balanced equations for or word equations for. And below are a few. Now this isn't an exhaustive list. There are going to be some that crop up that aren't on this list, but these are the most common ones. So number 1, the combustion of hydrocarbons. Now this comes up in topic 7 and it also comes up in topic 9, so it's quite likely you will come across either a word equation or a balanced simple equation for combustion. So this is complete combustion. You won't be expected to write an equation for incomplete combustion, but you would be expected to perhaps balance one that's already been constructed for you, or perhaps to describe or talk about an equation, but you wouldn't be expected to create one. So complete combustion is always hydrocarbon plus oxygen forms carbon dioxide and water. We have metals and oxygen. Metal plus oxygen goes to metal oxide. That one's pretty self-explanatory. And then we have metals with water, metals with acid. Now this all comes up twice as well. This comes up in topic 4 when we're talking about the reactivity of metals. It also comes up in topic 4 when we're talking about neutralization reactions. It also, a lot of these come up in topic 6 when we're talking about rates of reaction. Most of those reactions we look at tend to be neutralization reactions. So, these are the most common equations you're going to come across. So metals and water. Now the best example of this one would be the group 1 elements when they react with water, because not all metals react with water, only the really reactive ones do, which is mainly group 1 and a couple of the group 2 metals. but metal plus water goes to metal hydroxide plus hydrogen. And remember, we should have seen that when we added lithium, when we added sodium, when we added potassium to water, we got them fizzing around, hydrogen gas being produced, and the solution turning alkali because of that hydroxide. Metals and acid produce salt plus hydrogen. Now remember, salts are ionic compounds formed from the metal and the anion from the acid. So let's say, for example, this was iron metal and hydrochloric acid, it would form iron chloride as our salt. So naming the first half of the salt is very easy. You just find the metal, and the second half depends on the acid. If it's hydrochloric acid, then it ends in chloride. If it was sulfuric acid, it would end in sulfate. If it was nitric acid, it will end in nitrate. Metal carbonates an acid. So this is technically a neutralization reaction, but it does have an extra product. It has carbon dioxide because it is a metal carbonate. So metal carbonate plus acid goes to salt, water, and carbon dioxide. And then we have all acids and all bases. Now when we're talking about bases, we are talking about metal oxides and metal hydroxides. Metals on their own obviously have a slightly different reaction because they produce hydrogen rather than water. So only metal oxides and metal hydroxides produce salt and water. And metal carbonates are technically a base, but I've written them separately because they have an extra product. Now before we can construct balanced symbol equations, we first need to construct word equations. So the first one we're going to have is the combustion of butane. So following those general reactions we looked at on the previous page, so for butane, it will be butane plus oxygen goes to carbon dioxide plus water. Potassium and water, so this is a metal plus water, so it's going to be potassium plus water goes to potassium hydroxide plus hydrogen. Magnesium and oxygen, so this one is a metal plus oxygen, so it's just going to be magnesium plus oxygen goes to magnesium oxide. Lithium and sulfuric acid, so this is metal plus acid, which gives us salt plus hydrogen, so lithium plus sulfuric acid. Now the salt in this case will be the metal, which is lithium, plus the anion from the acid, so this is sulfuric acid, so it's going to form lithium sulfate and hydrogen. Calcium hydroxide and nitric acid, so this is a metal hydroxide, so this is a base, so this is acid plus base goes to salt plus water. So we've got calcium hydroxide plus nitric acid, and so our salt is going to be calcium because that's the metal, and the anion from nitric acid is nitrate, so it's going to be calcium nitrate plus water because it is a neutralization reaction. Copper oxide plus hydrochloric acid, again metal oxide, that is a base, so it's going to be a very similar reaction. So copper oxide plus hydrochloric acid is going to give us copper, chloride and water, and it gives us copper chloride because it's hydrochloric acid. And finally, sodium carbonate plus nitric acid. And again, this is a neutralization reaction, so it's going to be a salt produced, so sodium, and it's nitric acid, so it's going to be sodium nitrate plus water. But because it is a carbonate, we are also going to get carbon dioxide. So we need to be able to construct word equations, and that's purely learning and remembering the general reactions that we've covered throughout this whole course. So we've covered combustion reactions in topic 7, and then we've recovered them again in topic 9, chemistry of the atmosphere. We've covered metals and water and metals and oxygen when we did topic 4, the reactivity series, but you've also come across metals and water in the context of group 1, the alkali metals. And we've got all of the neutralization reactions, the metal oxides, metal hydroxides, metal carbonates with acid. We cover all of that in topic 4, the acids and bases topic, but we also come across it quite a lot in topic 6, the rates of reaction topic. So you've had quite a lot of exposure to all these different reactions by now, and you need to start committing them to memory so that when you see, potassium and water, you know it's going to form potassium hydroxide and hydrogen. Because if you can't write the word equation, then it's going to be very difficult to construct the symbol equation. So the first step to writing equations is to know the word equation first, and then you need to replace the names or the words with the chemical formulae. Now in lesson 1 we practice that. Now there are a lot of covalent formulas you just need to know, but there are a number of ionic formulas that you need to be able to work out. So we'll start with the combustion of butane. So this is one that we can work out. So butane is an alkane, and it is but, so that is 1, 2, 3, 4 carbons. So it's going to be C4, and because it is ane, that tells me it's going to have twice as many hydrogens as carbons plus 2. So that's going to be C4H10 plus oxygen, which is O2, which is one of the ones you need to memorize. And we know that is going to form carbon dioxide, which again is one that you need to memorize, and water, once again, one that you need to memorize. Now I'm not going to balance them yet, because it's impossible to balance a simple equation if the formulas are incorrect. So for now we're just going to practice making sure we put the correct formulas into these equations, and then we're going to come back and balance them. So potassium and water. So potassium, the symbol K. Always double check the periodic table. A common mistake is when people see potassium they put K, when they see sodium they put S, but you have a periodic table in the exam with you at all times. Just double check it so you're not making any of these silly mistakes. Water, H2O, and it's formed potassium hydroxide, KOH. Now again, this is one of the ions you need to know. The hydroxide ion is -1. You need to know that and memorize that. And potassium, we can look up the ion. It's in group 1, it's a metal, so it's going to be +1, meaning that the formula is just KOH. There's a 1-to-1 ratio. Magnesium and oxygen, Mg for magnesium, O2 for oxygen, and magnesium oxide is MgO. Now we can get Mg from the periodic table. O2 is one of the diatomic elements you just need to know, and this needs to be correct. How do we know it's MgO? Well, magnesium is in group 2 and it's a metal, so it's going to be +2. The oxide is in group 6 and it's a non-metal, so it's going to be -2. +2 and -2 cancels to 0, so the formula must be MgO. Right, lithium and sulfuric acid. So lithium Li, sulfuric acid, you need to know this formula, H2SO4. It is going to form lithium sulfate and hydrogen. Now we know the formula for hydrogen, we need to know the formula for sulfuric acid. Lithium we can get from the periodic table, but lithium sulfate we need to work out. Now we need to know that the sulfate ion is SO4 in brackets 2-, and lithium is in group 1, so it's 1+. So we've got a 1+ and a 2-, so in order to balance that we need 2 lithiums. Right, the next one, calcium hydroxide and nitric acid. Now again, we need to know the hydroxide ion, and we need to know that it's 1-, and the calcium is 2+ because it's in group 2, so I need 2 hydroxides to balance that. Nitric acid is one of those ones you need to know. You need to know that nitric acid is HNO3. It's going to form calcium nitrate. And again, you need to know that the nitrate ion, NO3, is 1 minus, and the calcium we already know is 2 plus, so we need 2 of those. And this is a neutralization reaction, so it's going to produce water. Copper oxide and hydrochloric acid is going to produce copper chloride and water, again neutralization reaction, metal oxide plus acid. And then finally sodium carbonate, Na2CO3, and again CO3 is one of those ions you need to know. Carbonate is CO3 2 minus. Sodium's in group 1, so it's only 1 plus, so I need 2 of them to balance it. Nitric acid, again you need to know the formula, meaning it's going to form sodium nitrate. Now we just said that the sodium was 1 plus, the nitrate we need to remember is 1 minus, so they balance, so you don't need any multiples. It's going to form water, but because it's a carbonate, you're also going to get carbon dioxide, CO2. Now again, we're going to come back later and balance these. For now, we're just interested in making sure that we get the correct chemical symbols or the correct formulas into the equation, because balancing it is not possible if any of these are incorrect. So we need to make sure that we are comfortable with getting the correct formulas into the equation before we can start balancing it. So once we have the chemical formulae in the equation, we can now look at balancing it. So what we're trying to achieve is we want the same numbers of atoms of each element on both sides of the equation. So if I've got 1 magnesium on the left, I need to have 1 on the right. So you have to have the same number of each atom of each element on both sides of this equation. Because the atoms aren't disappearing anywhere, they're not being destroyed and they're not being created, they're just being rearranged into new substances, and bonds breaking, bonds forming. The atoms aren't themselves being destroyed or created. So there must be, if you started with 4 carbon atoms, you must end up with 4 carbon atoms. They can't disappear and they can't suddenly become a larger number. So that's the first thing you're trying to achieve. The second thing is assuming you have got all the correct formulas in there, because if you haven't, you've already made the task impossible. So you can't change the formulas. So everything written here, so MgCO3, I'm not allowed to change any of that. I can't make it Mg2CO3. I can't cross out that 3 and make it CO2. So you can't change any of the formulas. The formulas have to stay exactly as they are. All you can do is change how many of each substance you have. So you can put multiples, you can put numbers in front of them to show that you want multiples of that substance. So an easy way to sort of train yourself not to edit the formulas is to draw circles around them. So I'm going to draw circles around them so that I know I'm not allowed to change anything in the circle. I can only put numbers in front of the circles. So let's start off with our elements. Now the trick here is to start with an element that only appears in one place on both sides. So it only appears in one place on the left on the reactants, and it only appears in one place on the right in the products. So a bad example, so oxygen would be a bad one to start with, because oxygen appears in 2 different places in the reactants and 1, 2, 3 different places in the products. So that'd be a really bad choice to start with the oxygen. So I'm going to start with the magnesium, because the magnesium appears once in the reactants and once in the products. So I've got 1 magnesium, 1 magnesium. So the magnesium is balanced. Then I'm going to look at the carbon, because I've got 1 carbon. The carbon only appears in one place on the left, and it only appears in one place on the right. So I've got 1 carbon, 1 carbon. So that looks good. Next, I'm going to look at the hydrogens. I've got 1 hydrogen here, but I've got 2 over here. Now again, I can't change anything in the circle, so I can't add a 2 there, and I can't scribble that 2 out. All I can do is put a number in front of that circle. So if there's 1 in the circle, I'm going to need 2 of them. That now gives me 2 hydrogens. by doing that, I don't just have 2 hydrogens, I've now doubled everything in there. So let's look at the nitrogens now. Used to have 1 nitrogen, but now I've got 2 of them. And over here, I've got 1 nitrogen in the bracket, but I've got 2 of the bracket, which means I do actually have 2 nitrogens. So that's balanced. So the magnesiums are balanced, the carbons are balanced, the hydrogens are balanced, the nitrogens are balanced. I've just got to check the oxygens. I've got 3 here, and I've got 2 lots of 3 here. So I've got 9 on the left, and over here I've got 2 lots of 3, so that's 6, 7, 8, 9, balanced. The next example then, aluminium hydroxide and sulfuric acid. Now I'm going to do the same thing. I'm going to draw circles around so that we know we don't change anything in the circle. We don't change the formulas of any of those compounds. And I'm going to start with aluminium because it only appears once on the left and once on the right, so that's a good one to start with. So I've got 1 here, but I've got 2 here. So I need to put a 2 in front of that circle there. I'm then going to look at the sulfur, because the sulfur only appears in one place on both sides. So I've got 1 sulfur here, but over here I've got 3, because I've got 1 in the bracket, but I've got 3 lots of brackets. So I've got 3 sulfurs here, but only 1 over here. And the only way to fix that is to put a 3 over here. Next, I'm going to look at the hydrogens. So in total over here, I've got 3 hydrogens in the circle, but I've got 2 lots of that. So I've got 6 hydrogens here. And again, I've got a 2 in the bubble, but I've got 3 outside. So I've got another 6. I've got 12 in total. And over here, I've only got 2. So I've got 12 over here, but I've only got 2 over here. So this must be 6 H2O, because 6 times 2 is 12. And then all that leaves is the oxygens. Again, I've got 3 oxygens here, but I've got 2 lots of aluminium hydroxide. So 2 3s is 6. And I've got 4 here, but I've got 3 lots there, so that's 12. So 12 plus 6, that's 18 in total over here. Then over here, I've got 3 times 4, which is 12, plus 6, which is 18, so it's all balanced. So let's have a look at these examples here. Balance the following symbol equations. Now, I'm not going to draw the circles because we should know by now that we don't change the formulas of our compounds. We are simply putting numbers in front of them. That's all we're allowed to do. So, combustion reactions, really simple. They're the easiest ones to balance because you just look at your hydrocarbon. How many carbons does it have? 1. So we need 1 CO2. How many hydrogens does it have? 4. So you need half as many H2Os because H2O's got 2 hydrogens. So if I've got 4, this is 2. If this was 6, this would be 3. If this was 12, this would be 6. It's that simple. So how many carbons do you have? That tells you how many carbon dioxides you need. How many hydrogens do you have? You need half as many water molecules. And then you've just got to add up all of the oxygens on the right. So I've got 2 plus 2 is 4. So how many O2s do I need to get 4? I need 2 of them. The next one, calcium plus water goes to calcium hydroxide and hydrogen. So I'm going to start with the calcium because it appears only once on both sides. 1 calcium, balanced. Next, I'm going to look at the oxygen. 1 oxygen, 2 lots of 1 oxygen. So I've got 2 here, but only 1 here. So I need 2 H2O. And then we can check the hydrogens. 2 lots of 2 is 4 hydrogens there. I've got 1, 2, 3, 4. Done, balanced. Potassium plus oxygen goes to potassium oxide. 1 potassium here, 2 potassiums there. So that's not going to work, is it? So I'm going to have to put a 2 in front of that. 2 oxygens, only 1 oxygen. So actually I need to put a 2 in front of this, which means I've got to go back and double check my potassium, because I said there was 2 before, so there's 2 there, but how many are there now? 2 lots of 2, there's actually 4 now. So sometimes you're going to balance one of your elements or one of your substances and then have to go back and change it. That's completely normal, and it's really important that you do go back and make those changes if you need to. So we balanced the potassium to start with, which gave us a 2, but then when we balanced for the oxygen we realized we needed twice as many potassium, so we had to go back and edit it. It's really useful to do this in pencil first, and then it's a little bit less messy if you do need to change any of them. So this one here, sodium, there's 1 on the left, but there's 2 on the right, so I need to balance that. Next I'm going to look at the sulfur. There's 1 here, there's 1 here. The hydrogens, there's 2 here, there's 2 here. The oxygens, there's 4 here, there's 4 here. So that one's nice and easy, already balanced. The magnesium, 1 and 1, that is balanced. Next I'm going to look at the nitrogen, and again I'm jumping to the nitrogen because it only appears in one place on both sides. You don't have to start left to right, so it's not like you have to do magnesium, then oxygen, then hydrogen. I just pick the elements that only appear once on both sides. If you do them first, it usually, by doing that, you will balance the other elements without having to think about it. So I did magnesium first because it only appears once on both sides, it was already balanced. Then I went for the nitrogen because that also appears once on both sides. I've got 1 on the left, but I've actually got 2 on the right, so I need 2 HNO3. Now you can look at the oxygens and the hydrogens. So we'll look at the oxygen first. So I've got 2 here, plus 2 lots of 3, so 6, plus 2 is 8. And over here, 2 3s are 6, plus 1 is 7. So that isn't balanced, but if I had 2 of those, it would balance. And then let's double check the hydrogens. I've got 2 here, and I've got 2 there, so that's 4 in total, and 2 lots of 2 is 4, so that is balanced. So the copper oxide, 1 copper, 1 copper, balanced. 1 chlorine, 2 chlorines, so I need 2 HCl, 1 oxygen, 1 oxygen, 2 hydrogens, 2 hydrogens, done, balanced. And then the last one then, beryllium carbonate with nitric acid, so 2 berylliums on the left but only 1 on the right, so we need 2. Then I'm going to go for the carbon because it only appears once on both sides, 1 carbon, 1 carbon. Then the nitrogen, 1 nitrogen, but I've got 2 on the right because I've got 2 lots of NO3, so I need a 2 there. And then we can check the hydrogens and the oxygens. So I've got 2 hydrogens, 2 hydrogens, 3 oxygens, plus 2 lots of 3, so 9 in total. 2 lots of 3, so that is 6, 7, 8, 9. Balanced. So now we can go back and have a look at the word equations that we constructed earlier and the symbol equations that we constructed earlier. And now that we know that they're correct, we can start to balance them. So the first one, we have a combustion reaction. Now again, as I said before, look at how many carbons in the hydrocarbon. That tells you how many carbon dioxides you need. Look at how many hydrogens in the hydrocarbon, and you need half as many water molecules. And then you've just got to add up the total number of oxygens on the right. So we've got 2 lots of 4 is 8, plus 5 is 13. Now, unfortunately, we've got ourselves an odd number, but we can simply just put 6.5 O2. Now, obviously you can't have half an oxygen molecule, but this is just a ratio, okay? So if you're unhappy with the 6.5, then just double all of them. So it would become 2, 13, 8, 10, and then you've got whole numbers. It's just a ratio, okay? So don't get hung up on the fact that it's half an oxygen. So potassium and water. So 1 potassium, that is balanced. 2 hydrogens, 1 hydrogen, that is not balanced. It's just occurred to me we're missing something here. So this is what I'm talking about. If you If you get the symbol equation wrong, then you're already stuffed. We are missing some hydrogen. 1 potassium, 1 potassium, 2 hydrogens, 1, 2, 3 hydrogens. That doesn't work, so we need 2 of those, which means we need 2 oxygens, which means we need 2 potassiums, but that should now be balanced. So 2 potassiums, 2 potassiums, 2 oxygens, 2 oxygens. That gives us 4 hydrogens, 1, 2, 3, 4, all balanced. Obviously, you need to have the correct symbols and the correct symbol equation first, otherwise balancing it is impossible. Magnesium and oxygen, 1 magnesium, 1 magnesium, balanced. 2 oxygens, 1 oxygen. Remember, we can't just tack a little 2 on there. So if I've got 2 here and only 1 here, I'm going to need 2 MgO, which means I need to go back and I'm going to need 2 magnesiums. Lithium and sulfuric acid, 1 lithium, 2 lithiums, so I need 2 over here. I'm going to ignore the, oh no, we can do the hydrogens, 1, 2, 1, 2, hydrogens are balanced. Sulfur, 1, 1, balanced. Oxygens, 4, 4, balanced. 1 calcium, balanced. I'm going to ignore the oxygen because it is all over the place. There's an oxygen here, there's oxygen in this one, there's oxygen here, oxygen here. I'm going to ignore that. I'm going to ignore the hydrogens as well because they're split across multiple, 3 different places hydrogen turns up. Nitrogen, once on the left, once on the right, so that's going to be my second focus. So calcium, 1 and 1, nitrogen, 1 here, but I've got 2 here because I've got 2 lots of the bracket, so I need 2 HNO3. Now I can look at the hydrogens and the oxygens. So I've got 2 hydrogens, done, balanced. That's not correct, is it? I've got 2 hydrogens, I've still got 2 here. Sorry, I've got 4 hydrogens, 2 hydrogens, that is not balanced. I need 2 of those. Oxygens, 2 lots of 3, it's 6, plus 2 is 8. Over here, 2 lots of 3 is 6, plus 2 is 8. That is balanced. 1 copper, 1 copper. 1 hydrogen, 2 hydrogens. 2 chlorines, 2 chlorines. 1 oxygen, 1 oxygen. Balanced. Sodium carbonate and nitric acid. So I've got Na2, but only 1 over here, so I'm going to need 2 of those. 1 carbon, 1 carbon. 1 nitrogen, 1 nitrogen. Sorry, 2 nitrogen, sorry, because I've got 2 of this, haven't I? So I need 2 of these. 2 hydrogens, 2 hydrogens. 2 3s is 6, plus 3 is 9 oxygens. 2 3s is 6, 7, 8, 9 oxygens. The last thing we're going to do then is just quickly map out that process as a flow map for writing balanced simple equations. So number 1, you need to write out the chemical formulae for all substances in the reaction. And as we saw earlier, you need to double check it, because if you get this section wrong, then balancing it will become impossible. And then simply we're going to add large numbers in front of the formulae if needed to balance the number of atoms of each element. And we're going to make sure we do not change the formulae. Water is H2O. You're not going to be able to change that formulae. Carbon dioxide is CO2. You can't change that formulae. Magnesium oxide is MgO. You need to keep the formulae correct as they were and balance it simply by adding large numbers in front. If you're finding that it's impossible, then maybe that could be a sign to show that you've made a mistake, just like in the example earlier with the potassium and the water. I saw very quickly that that wasn't going to balance, and it's because I'd forgotten the hydrogen. So if you're struggling to balance it, then maybe check the formula. You might have made a mistake. So what we need to add to this is we should start by balancing elements that only appear once on both sides. There will usually be one or two elements that only appear once in the reactants and once in the products. They're going to be the easiest ones to balance first, but also do not forget that sometimes you might have to go back and rebalance something, because by changing it later on you've actually adjusted the total number of an element you'd already balanced, and now it becomes unbalanced. So you have to go back and double check all elements at the end. So double check all elements are still balanced at the end. And then we have some simple equations for you to balance.